Okay, so now we're going to talk about a formula used to calculate the probability of a single value for a binomial random variable. So again, understand when we're talking about binomial random variables, we are talking about the count of successes, right? So the number of successes, that's what our variable represents, the number of successes. And your number of successes can take on any value between 0 and n. And again, this is why I consider this more of a discrete case, because notice that these are all whole numbers, right? It cannot be any value. It's certain values, but it goes all the way from 0 to n. 0 meaning no successes, n meaning all successes. Okay, so here is our binomial probability formula. It's a biggie. So again, suppose you have n trials, probability of p for a success. If we want to get exactly k successes, then here is our fun formula. So the probability of our random variable equaling k is equal to n choose k times p to the k times 1 minus p to the n minus k. Oh my goodness, what is that? Well, if you look down here, what I've tried to do is I've tried to give you an idea of what that formula means. So the probability of getting exactly k successes, sorry, I left that word out, is equal to, well, the n choose k is the number of ways to get k successes in n trials. Again, order doesn't matter. We just want this number of successes times, and now the p to the k is p, the probability of success, times k, the number of successes. And we'll talk about how when you had independent probability, you would take the probability and multiply it by the next probability. Well, if I want k successes, it's p times p times p k times. And again, we'll show that in the next example. And then the 1 minus p is the failure. Again, when you use the word not, like we did in our Benz examples, that's the complement. And the complement of something is 1 minus that thing. Okay, so that's the probability for a failure. And then the n minus k are the number of failures, right? Because if you have n things and you want k successes, then n minus k is the number of failures. Okay, so hopefully this formula makes sense a little bit, and you can use it going forward. Again, do not memorize this. Remember where this formula is, write it down on a piece of paper and use it. Okay, example 2. How do we inherit blood type? Genetics say that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has probability of 0.25 of having type O blood. Suppose these parents have 5 children. Find the probability of exactly 3 of them having type O blood. Okay, so again, we are looking for the probability of exactly 3. So probability that exactly 3 out of the 5 children have type O blood. Okay, so when we do this, right, let's let x be our random variable. So x is the number of children with type O blood, right? You don't have to do this, but I'm doing this, right? So we want to find the probability that our variable is equal to exactly 3. Well, we have to figure out the number of ways to get 3 children out of 5 to have type O blood. Well, in this problem n, the number of trials, or the number total, is 5, and k, our number of successes, is 3. So we're going to start with 5, choose 3, times, and now we want 3 of the children to have a type O blood. Well, 0.25 is the probability of having a type O blood. Our p-value is 0.25. So watch what I'm going to do. I'm going to do 0.25, so that's 1 child, times 0.25, that's 2 children, times 0.25, that's 3 children. That's 3 children having type O blood. Again, if this is a true binomial situation, those are independent probabilities. To find the probability of them happening together, we just multiply them. Right? But there are 5 total children. 3 of them have type O blood. That means that 2 of them are not going to have type O blood, right? K minus n is, n minus k is 5 minus 3, so that's 2. And to find the probability of not having type O blood, we're going to take 1 minus 0.25. and that's 0.75. So now I need to line up times 0.75 times 0.75. So this right here, this is the elongated formula. Okay. And again, we did this part right here back in section 4.6 when we learned the multiplication rule for independent events. And again, this was 4.8. Right? So now our formula now says this. The probability of x equals k, and k is 3, is equal to n choose k. So we know that's 5 choose 3, right? 5 choose 3 times p, the probability of a success, to the number of successes power 3. And again, that's because when you multiply 0.25 3 times, that's what it is, exponent rules, right? Times, and now this is 1 minus 0.25 raised to the n minus k. But we just figured that out, right? It's 0.75 raised to the second. And now notice a couple things. When you do this, these two probabilities add to 1, and these two exponents add to 5, which is your n value. And this number here matches that number there. So again, there's a lot of ways to remember how to use this formula. Okay. So now I'm going to show you how we type all of this in to the graphing calculator once I take a picture of it, because I don't know if I'll remember it. All right, cool. All right, so let's do it. Okay, so this is going to go away. And again, we're still just trying to find the probability of exactly 3 of these children having type O blood out of the 5. Okay, so I go to my graphing calculator. So remember, we start with n, choose r, n, c, r. Remember, r is k. We want 5, comma 3 times. Okay, and now we're going to do 0.25 raised to the third. Then you can use, if you get the keyboard here, you can use the AB button as well, times 0.75 raised to the second. And this is the probability that I'm looking for. Okay, we're going to go ahead and round it to, we'll go 4 decimals. So 0.0878, the 9 makes this 8 become a 9, 0.0879. That is the probability that exactly 3 of these 5 children would have type O blood. Okay, so that's our probability of x equaling 3. All right, good. So hopefully that made sense to you. Again, don't let the formula confuse you. It's not confusing. It's just using stuff from chapter 4. All right, good luck.